recording. The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I will respond as soon as I can. All right, eventually today we're going to be going on to section 11.2, but first we have some questions from 11.1. So let's take a look at that. This is question number 8 from 11.1. It says, let f of x equal 8x plus 4 and g of x equal x squared minus 6. Find the following. G composed with f of 6x. So g composed with f of 6x is equal to g of f of 6x. So first of all, we need to find f of 6x. F of 6x would be 8 times 6x plus 4, which is 48x plus 4. So we put 6x in the place of x in the f of x function. We simplify it, we get 48x plus 4. So then this quantity replaces f of 6x. So far, so good?
Yes.
So now we've got g of 48x plus 4. So we're going to take the g of x function and evaluate it at 48x plus 4. So that would be 48x plus 4, the quantity squared minus 6, because again, we've got x squared minus 6. But that gives us 48x plus 4 foiled with 48x plus 4 and then a minus 6. Let's see. What's 48? 48 times 48 is, we get 2,304 x squared plus 48 times 4 is 192x plus 192x plus 16 minus 6, which is 2,304x squared plus, let's see, 192 times 2 is 384x plus 16 minus 6 would be plus 10. So there is our huge final answer. Seems kind of intimidating. You might have come up with that and thought that can't be right, it's too big, but that's the answer. Right? We good to go on to number 9?
Yes.
Okay, so this is still in 11.1, number 9, and it says, let's see here, let f of x equal 9x plus 9 and g of x equal x squared minus 5. Find the following. F composed with g of 3x. F composed with g of 3x equals f of g of 3x. G of 3x equals 3x, the quantity squared minus 5, which would be 9x squared minus 5. So that gets substituted in the place of g of 3x, which gives us f of the quantity 9x squared minus 5, and that's going to go in here. So that's equal to 9 times the quantity 9x squared minus 5 plus 9, which is 81x squared minus 45 plus 9, or 81x squared minus 36. So there's that situation. We good to go with that?
Yes.
Yes.
All right. And finally, here comes 11.1 number 16. It says, let f of x equal 3x minus 9 and g of x equal x squared plus x. Find g composed with f of x. G composed with f of x. So that would be equal to g of f of x. But f of x is 3x minus 9. So that goes in the place of f of x. So now we need g of 3x minus 9, and that's going to go in here. So that's equal to 3x minus 9, the quantity squared, plus 3x minus 9. So we've got 3x minus 9 times 3x minus 9 plus 3x minus 9, which is 9x squared minus 27x minus 27x plus 81 plus 3x minus 9, which is 9x squared. Let's see, minus 54x plus 3x would be minus 51x, and then plus 81 minus 9 would be plus 72. So 9x squared minus 51x plus 72. All righty.
I see what I did wrong on those problems.
Okay, well, good. We've set you straight. Anybody, any questions other than the ones I just covered?
No.
Then we will continue on to section 11.2. And today, the big topic is inverse functions. And let's see, also the idea of one-to-one functions. Let's start out with what a one-to-one function is. Okay, let's say we've got 1, 2, 3, 4, and range 5, 6, 7. Okay, let's say that 1 goes to 5 and 2 goes to 5 and 3 goes to 6 and 4 goes to 7. This is a function in that for each value in the domain, there is exactly one value in the range, but it's not a one-to-one function because there are two values in the domain going to one value in the range. Let me give you an example of a one-to-one function. Let's see here. 3, 4, 7, 9, 2, 8, 1, 6. Let's say we've got this situation where each value in the domain is going to exactly one value in the range, but each value in the range is only connected with one value in the domain. So we get that one-to-one correspondence, okay? So whereas this is a function, this is a one-to-one function, all right? Now, when you have a one-to-one function, there's something called an inverse function. If the function is one-to-one going that direction, where this is the domain and this is the range, if we go back the other direction, that would be the inverse. And if the original function is one-to-one, the inverse is also one-to-one, because if we take all of these values and we connect them, so if we change this to the range and this to the domain and we go back the other direction, it's still a function. Okay, so if a function is one-to-one, there exists an inverse function where the domain of the original is the range of the new and the range of the original is the domain of the new. So the domain and the range interchange. Little poem there. The domain and the range interchange with a one-to-one function. I probably should keep my day job though. All right. Look at this though. Here, if we declare this the domain and this the range, it's not a function because you've got one input going to more than one output. So only a one-to-one function has an inverse function. Okay. Let's see here. Hang on a second. I know what I want to talk about. Let's take a look at some graphs for a minute. Okay. This is the graph of a function because it passes the vertical line test. However, it is not a graph of a one-to-one function because it fails the horizontal line test. So if a function is one-to-one, you can pass vertical lines through it and never cut through it more than once. You can pass horizontal lines through it and never cut through the graph more than once. So for instance, let's see here. That would be a one-to-one function because it passes the vertical line test, meaning it's a function, but it also passes the horizontal line test. So this is a one-to-one function. Okay, so if a function is one-to-one, the graph will pass both vertical line tests and horizontal line tests. If it fails either of these tests at any point, it's not a one-to-one function. Okay, now, hang on, let's see here. If a function is one-to-one, then it has an inverse, which is also a function, which is also one-to-one. And I know I kind of said most of that earlier, but I'm going to keep repeating a lot of things here. There is a way algebraically to take a one-to-one function and find its inverse function. That's what we're going to look at next. Okay, so let me see here. Let's take this. F of x equals 2x plus 4. Tell you what, let's look at the graph of that for a minute. F of x equals 2x plus 4. That would have a y-intercept of 4 and a slope up 2 and over 1. So basically, it would look like, let me get this lined up here. It would look like that, okay? Is that a function? Yes, it passes the vertical line test. Is it a one-to-one function? Yes, it passes the horizontal line test. So this function is one-to-one. Let's find its inverse function. Step number 1. Replace the function notation with regular equation notation. So in other words, replace f of x with y. Okay, that's step number 1. Replace whatever function notation f of x or g of x or whatever it is with y. Okay. Step number 2. Interchange all the x's with all the y's in the equation. So now I get x equals 2y plus 4. So I just switched all the x's with all the y's. What I have now is the inverse function. Okay, but I'm not done yet. All right. Step number 3 is to solve this new equation slash function for y. So I'm going to subtract 4 from both sides of the equation. I'm going to divide by 2. Whoops. So I get x minus 4 over 2 equals y. I'm going to turn it around and just put y over on the left side of the equation, just because that seems to be the nicest place to put it. I didn't change anything. I just put y on the left instead of on the right. Okay, so that was step 3 to solve the new equation for y. Step 4 is to go back to function notation, only now we're going to use the inverse function notation, which looks like this. Now, that looks like f to the -1 of x, okay? It's not. That -1 is not an exponent, so then you get 1 over f of x, okay? It's notation used to mean the inverse of f, okay? So this is the original function. This is its inverse, okay? Again, the 4 steps were, step number 1, replace f of x with y. Step number 2, interchange x and y. Step number 3, solve the new equation for y. Step number 4, replace y with the inverse function notation. Okay. Any question about those 4 steps? And I'm going to go back and do some more examples in a bit, but I want to take this further. Okay. So let's go back and let's see what we can do here. Let's recopy those on the next page. So we've got f of x equals 2x plus 4, and f inverse of x equals x minus 4 all over 2. Okay. I want to look at some things to do with a function, a one-to-one function and its inverse. First of all, let's make a table of values for f of x equals 2x plus 4. And let's find, maybe 4 points. How about if we use -1, 0, 1, and 2? And there isn't any specific reason I picked those other than they're just kind of small numbers. All right. If x is -1, then f of -1 would be 2 times -1 plus 4, which is -2 plus 4, which is 2. Okay. If x is 0, f of 0 would be 2 times 0 plus 4, which is 4. If x is 1, f of 1 would be 2 times 1 plus 4, which is 2 plus 4, which is 6. If x is 2, f of 2 would be 2 times 2 plus 4, which is 4 plus 4, which is 8. Okay, so there are 4 ordered pairs that are solutions to f of x. Any question about those?
No.
All right, what I'm actually going to do here, I should have done this to start with. I'm going to erase this and I'm going to write it using red. Okay, so let's do the inverse in red. I'm going to pick the following x values: 2, 4, 6, and 8. Okay. I just felt like picking those out of thin air. Maybe. If x is 2, then f inverse of 2 would be what? 2 minus 4 over 2, which is -2 over 2, which is -1, correct? Okay. If x is 4, f inverse of 4 would be 4 minus 4 over 2, which is 0 over 2, which is 0. F inverse of 6 would be 6 minus 4 over 2, which is 2 over 2, which is 1. What do you think f inverse of 8 is going to be?
2,
Where'd you get that?
because 8 minus 4 is 4 over 2, which is 2.
Oh, so you just figured it out that way. I was hoping that maybe you were peeking over here.
Oh, I guess I could have looked over there too.
That's okay. That's okay. So this should not be a big surprise because remember how we found the inverse function? We interchanged x and y. So that means that the domain over here would be the range over there. And the range over here would be the domain over there. So all of our ordered pairs from f of x, the x's and y's are switched for the inverse. Okay? All right. Now, let's do something else here. And let's see if I can do this without a major catastrophe. I'm going to write down what I've got there because I'm going to refer back to it here in a minute. So for f of x, my ordered pairs, let's see, we've got -1, 2, 0, 4, 1, 6, and 2, 8. For f inverse of x, I've got 2, -1, 4, 0, 6, 1, and 8, 2. Okay. Now I'm going to go back here to, let's see, let's go here and let's delete or erase. Oops, come on, eraser. Don't fail me now. I erased more than I wanted to there. That's okay. We'll fix it. Here. So let's see, this is 5, and this is -5. Okay, now, actually, there's only 3 of these points I can plot there. For f of x, tell you what, let me do this. Let me write these table values. I'm just going to use 3 of them because the 4th one is not on the graph. The reason I'm doing this is because I have better luck using this program for graphing than the other one. So I try to avoid the other one when at all possible. Okay, so I've just copied 3 of the ordered pairs from f of x and f inverse of x. And again, I should have done this in red, and I will do that when I graph it. Okay, so f of x, let's see, x is -1, y is 2, x is 0, y is 4, x is 1, y is 6. Okay. So there is the graph of f of x. We okay with that? All right, now let's graph f inverse of x. X is 2, y is -1. Come on, get red there. X is 4, y is 0. X is 6, y is 1. And I will graph that. Let's see here. All right. So that's the graph of f inverse of x. Okay. Now, remember that each ordered pair for f of x, the x and y are switched to get f inverse of x. If we take the line y equals x, see if I can do this right, and we graph it, well, didn't quite make it, but almost. Can you see that f of x and f inverse of x are symmetric with each other about the line y equals x? Can you see that? Symmetry there? So, for instance, this distance is the same as that distance. This distance is the same as that distance. This distance is the same as that distance. And here, in fact, they overlap. Okay. So what that means is if you have a one-to-one function and you have its inverse function, all the ordered pairs from the original, if you interchange x and y, you get ordered pairs for the inverse. If you graph them, the two graphs are symmetric about the line y equals x. So in fact, if I had a one-to-one function and I had its graph, I could just draw the line y equals x, reflect it across the graph, and get the graph of the inverse function without actually finding it algebraically. Just a point of fact. Okay. Any questions?
No.
All right, let's go back to our two functions. Okay, and I'm going to recopy them on the next page. Again, f of x equals 2x plus 4. Let's see, f of x equals 2x plus 4. And f inverse of x equals x minus 4 over 2. When you have a one-to-one function and its inverse, if you compose f with f inverse, you get x as the final answer. If you compose f inverse with x, excuse me, f inverse with f of x, you also get x. Now, yesterday I said that composition wasn't commutative in general, but when you're composing a function and its inverse, then it is commutative. That is a one-to-one function and its inverse. Okay, so let's find f composed with f inverse of x. Okay, so that's equal to f of f inverse of x, which is equal to f of x minus 4 over 2. Okay, because this goes in the place of that. All right, but that's equal to 2 times the quantity x minus 4 over 2 plus 4. You following this okay? But these will reduce down, giving me x minus 4 plus 4. Those will cancel out, giving me x. So f composed with f inverse of x equals x. We're halfway home. And I should have written it over further so that I had more room, but oh well. So now let's find f inverse composed with f of x, which is equal to f inverse of f of x, which is equal to f inverse of 2x plus 4, which is 2x plus 4 going in the place of x, minus 4 all over 2. Well, the plus 4 and the minus 4 cancel. The 2's reduce down, and voila. So, at least for this one example, and it is true in general that a one-to-one function and its inverse function are, let's see, commutative in terms of composing them in both directions, right? In fact, if you had two functions, let's say f of x and g of x, and you wanted to determine is f of x and g of x, are they inverses of each other, you could compose them in both directions. And if they both equal x when simplified, that would be proof. Okay, what I want to do now is I want to go back and take another equation, another function, and find its inverse. Okay. All right. So let me see here. Where is it? Ah, here we go. F of x equals x squared plus 1. And then it says x is greater than or equal to 0. It's got that condition on it. Okay. All right. Let's find this function's inverse. All right. So step number 1, replace f of x with y. So y equals x squared plus 1. Step number 2, interchange x and y. So x equals y squared plus 1. Step number 3, solve for y. I'm going to subtract 1 from both sides. So I have that. I'm going to switch over and just put the y squared on the left side. Okay. So what would I do now to solve for y? Well, I'd take the square root of both sides of the equation. Don't forget the plus or minus, right? Okay. And then finally, step 4, rewrite using inverse function notation. F inverse of x equals plus or minus the square root of x minus 1. And there you go. There's a problem, however. Okay. So notice that there was a condition, and I just sort of ignored that on purpose for the moment. What I want to do, I want to go back. Let's see. Let's go back here and let's erase all of this stuff if we can. I needed to have more graphs than I made ahead of time, but oh well, we'll be fine. Okay. So let's see here. Here. We've got what? 5, 5, negative 5, negative 5. All right. Now, f of x equals x squared plus 1. What does the graph of that thing look like? Well, I can find it here. Doesn't it look like y equals x squared, but moved up 1 unit? So it would look like that. Okay, remember, y equals x squared is a parabola with the vertex at the origin, and then it's moved up 1 unit. So are you okay that that's the graph of x, of f of x?
Yes.
Okay, let me ask you this. Is that a one-to-one function?
No, I was confused. So
It's not a one-to-one function, is it? But what if we apply that restriction that says x is greater than or equal to 0? So then that means we get rid of this piece. You see that?
yes.
So we took a function, put a restriction on the domain in order to create a piece of function that is a one-to-one function. Okay? So far, so good?
Yes.
All right, now let's take a look at this thing. Okay. Now, I'm not going to go into great detail about how to graph it. I'm just going to go ahead and graph it here. And if you have questions, I'll be happy to answer them. But what that graph would look like notice that it has plus or minus the square root of x minus 1, okay? Plus the square root of x minus 1 would look like this. Minus the square root of x minus 1 would look like this. So putting the two pieces together, you get that. Well, not only is that not a one-to-one function, but it's not even a function. It fails the vertical line test, doesn't it? So let's see. If we put, I know life is getting complicated here. If we graph y equals x, oops, didn't get it to come through there. I need just this piece here, don't I? If I had just that piece, would that be 1-to-1? And would they reflect across the line y equals x?
Yes.
Okay, so let's go back here. Remember, the domain of the original function is the range of the inverse. The range of the original is the domain of the inverse, okay? Since we have a restriction x greater than or equal to 0 on the first function, what would the restriction be on its inverse? It would be y is greater than or equal to 0, which would have the effect of getting rid of that minus and would have the effect of getting rid of this piece. And voila, you've got a function that's 1-to-1, it's inverse, and they're symmetric about the line y equals x, okay? So by putting a restriction on the domain of the original, which then became a restriction on the range of the inverse, we created a 1-to-1 function and its inverse. How fun is that? Okay. What I want to do now is just go back and do some more of taking a 1-to-1 function and finding its inverse, because that typically is the thing that students are most confused by. Are we good to go on?
Yes.
All right. So let's see here. How about this one? F of x equals x minus 4 over 5. The directions say each of the following functions, each is 1-to-1. Find the inverse of each function and express it using f inverse of x notation. Okay? So they've already told us in the instructions that this is 1-to-1. Step number 1, replace f of x with y. Step number 2, interchange x and y. Step number 3, solve for y. How I'm going to do that, I'm going to multiply both sides by 5. On the left, I get 5x. On the right, the 5's reduce out and I get y minus 4. Then I'm going to add 4 to both sides and I get 5x plus 4 equals y, which I'm going to rewrite as y equals 5x plus 4. So I'm just turning it around so that I've got y on the left side. And then finally, I'm going to rewrite it using inverse function notation. So here is f of x, here's f inverse of x. Any questions about this particular problem?
No.
No.
Okay, let's take a look at another one. Let's see here. F of x equals 3 over x cubed minus 1. Step number 1, replace f of x with y. Step number 2, interchange x and y. So we get x equals 3 over y cubed minus 1. Step number 3, solve for y. Well, let's see here. Do you want to move the 1 over to the left first or multiply everybody by y cubed to clear the fraction? We can do it either way.
Move the 1 first.
Move the 1 first? Okay. So we're going to add 1 to both sides. So we've got x plus 1. And when I say we could do it either way, the other way might not be nice. So if I tried it the other way and then things were not looking good, I might go back and switch the way I'm going to do it. So now I'm going to multiply both sides by y cubed. So I've got y cubed times x plus 1 equals 3. Since I'm trying to solve for y, there would be no reason to distribute the y cubed. So I'm going to divide both sides by x plus 1. So I've got y cubed equals 3 over x plus 1. So far, so good?
Yeah.
What am I going to do now?
Write it in inverse notation.
But I haven't solved for y yet. I've solved for
you
y
have to
cubed. What do I need to do?
cube root.
Cube root. Okay. When I take the cube root, do I add that plus or minus, or is that just with even roots?
That's for all of them, isn't it?
Just with even roots.
Just the even?
Yes. You ever play Monopoly?
Yes, but I suck at it.
That's okay, but you know there's a sign that says, go directly to jail, do not pass go, do not collect $200. Go directly back to chapter 9 and review that idea. Or is it chapter, yeah, I think it's in chapter 9 we talk about it. Anyway, okay, enough of that. So we get this. Now we've solved for y. So f inverse of x equals the cube root of the quantity 3 over x plus 1. Okay. So again, when you take an even root of both sides of an equation, you put the plus or minus. When you take an odd root, you just get what it is.
Are we going to have to do any graphing on the homework assignment?
I'm trying to remember. I think it just has multiple choice pictures of, here is a graph of f of x, or is this a graph of f of x and its inverse, or is this a graph of f of x and its inverse, those kinds of things.
Okay.
I think it's just multiple choice. Do you want me to bring something up and check on that?
No, it's okay. It's just a little confusing on the graphing. So.
Well, okay, so 2 things to keep in mind. Your ordered pairs for f of x, take each x and y and interchange them. You've got ordered pairs for f inverse of x. So if you make a table for one, switch the x's and y's, you've got a table for the other.
Okay.
If you graph one, graph the line y equals x and then reflect it symmetrically, I don't know if that's a word, symmetrically, across that line.
Okay.
Okay, if you get stuck, you know where to find me. Let's do one more of these. Let's see here. F of x equals x minus 9 cubed. So to find the inverse, replace f of x with y. Interchange x and y. Solve for y. I'm going to take the cube root of both sides, which is going to give me the cube root of x equals y minus 9. Add 9 to both sides, the cube root of x plus 9, and the plus 9 is not inside the cube root, equals y. So y equals the cube root of x plus 9. F inverse of x equals the cube root of x plus 9. We've got 6 minutes left. I'm going to go ahead and go to WebAssign anyway. Let's take a look here. Just give me a minute to bring it up, as I'm pretty sure, if I remember correctly, it was multiple choice looking at graphing. Okay, so let's see here. I'm gonna go here and here. This is 11.2. I know you can't see it yet. Let me just get it up here first. Come on. Here we go. Okay. I noticed somebody sent me a message in the chat. I don't have time to look there. So if it was one of you, email me. Okay. All right. So look at number 27. Find the inverse of the function, then graph the function and its inverse on one coordinate system. Show the line of symmetry on the graph. So your original function is f of x equals negative 4x. And then you're supposed to find the inverse, which, can you see where it says negative x over 4?
Yes.
So that's the correct answer. It shows it on my view. In fact, it shows the correct answer here, but we'll ignore that for the moment. So then you're going to look down here. You've got this dotted line is supposed to be y equals x. Okay. And then you've got, let's see, it doesn't say which is blue and which is red, but so you're looking at these and you have to decide which one is the function and its inverse. Does that make sense?
Yes.
Now, here's another example. Find the inverse, then graph the function and its inverse, and it shows, so it's a multiple choice. Let's see here, same thing here.
Do any of them have the graphing one with the restrictions? Oh yeah, right there.
Ah, aha, yeah.
I think
So-
that's the most confusing part of this whole thing.
What's that?
That's the most confusing part of the whole thing is
The restrictions?
Yeah.
Okay. Well, for instance, here, x is greater than or equal to 0. That would just give you this purple part, not the blue part, right?
Yeah.
Okay. Anyway, all right. Well, that's enough torture of you for today. I'm sure you agree. So we'll stop the recording.